Okay, so it's a great pleasure actually to be invited to this 15th anniversary symposium at STAM. And it's also very nice to me to be on the campus of the University of Tokyo, maybe much more beautiful than UCLA in some ways. And I'm also happy to be the regional editor of STAM, I think, for a couple of years now. And I'd like to thank Professor Kishi, who was actually instrumental in me being in Japan so much. I come to Japan about 4 or 5 times a year as a part of the MEX WPI program called Material Nano Architectonics, which is based in NIMS and SCUBA, the National Institute of Material Science. So I was asked to give a talk, and the talk is aimed not at the people at the front, but more at the students at the back, which I can hardly see, but they're in the kind of darkness there, so I can't tell if they're awake or not. And it's not a purely scientific talk. It's about actually a kind of process. You know, when you talk about art, you talk about process. And actually, science is about process. It's about how do you develop creative ideas as well as have a kind of reductionist approach to experimental work. And I was lucky enough to actually, in the early part of my career, I guess, join IBM Zurich Research Laboratories in Ruschlikon, where in 1983 there were a couple of scientists there, Heinrich Rohrer and Gerd Binnig, who had some crazy idea how to build a microscope. And they were actually very, very imaginative people, and they really inspired me. So I'd like to in the first part of the talk about that and talk about something that is actually instrumental in the concept of nanotechnology. Nanotechnology as a word was actually invented by a Japanese, Norio Taniguchi, but it became a popular sort of field more or less around about after 1986, when the scanning tunneling microscope was able to see atoms and eventually manipulate them. And really, the scanning tunneling microscope, it was a career that lasted maybe 19 years in my life. And it was somewhat about reductionism. I mean, the ultimate reductionism, to look at what I imagined then was a single atom. I don't imagine a single atom now. I don't think a single atom is such, you can't look at it in a way. You can look at an atom, but it's a part of a much more complex interaction. And in 2001, I left IBM because I really wanted to kind of change my life or something like that. And since then, I've been at UCLA in the chemistry department, and also the California Nanosystems Institute, which is a very large and prestigious institute that's developed since 5 or 6 years. And my work changed from the idea of looking at an atom and this reductionist approach to more about a process which is inevitable in nature, and that is one of self-organization and the creation of a system that's not ordered, not completely chaotic, but somewhere in between. A system that is very much like the most advanced material in the world. And the most advanced material in the world is actually your own brain. So the talk is about building a brain, and you can take it in 2 ways. In one way, it's about the device we try to build, in both at UCLA and in SCUBA, in NIMS, but it's also about my own brain, because the process of doing science for 40 years has, of course, changed my brain quite a bit. So before the scanning tunneling microscope, you know, we go back to Schrödinger, who's a very famous person in quantum mechanics. He didn't believe that one could look at single atoms or electrons or molecules. And he mentioned, you know, the idea of beyond detection lies interaction. And so it was really a very radical kind of step when Gerd Binnig and Heine, who passed away, he loved Japan, he loved sashimi, and he would come here all the time, and we would sit and drink sake and so on, and have fun. They invented a device which was at first not believed. Most of the physics community, and it's hard to imagine for you now, really did not believe this device worked. It consisted of a sharp tip that was very close to the surface, such that electrons could sort of tunnel through, quantum mechanically interact, if you like. And they made an image here where they could see silicon atoms. And eventually, people really did believe this machine worked. And it enabled a person, as an extension of your own hand, to interact with an atom like it was this bottle of water or so, or to measure it by moving the finger over the bottle of water, except, of course, the finger was millions and millions of times smaller. And this is what it looked like. It was a big, ugly beast. And on the top there was a small component with the tip, and the rest was because of the vibrations in the room. Oh, I don't need it. I'll use it maybe, but. So I was actually a chemist originally, and when I joined IBM in the physics department, you know, it was quite daunting for me, but I really liked the sense of humor they had. And I came up with this idea that no one had, you know, it was a new microscope, very few people had it, and we had to build it. But could one look at a molecule? And it seems obvious now, you could look at a molecule, but in those days, for instance, the director of the Max Planck Institute in Berlin, the Fritz Haber Institute, he told me, no, you can never see a molecule. It's theoretically impossible. And many people told me it was impossible. But somehow I believed in the idea that you could see a molecule. And in 1986, we started this experiment several years earlier. We were able to image a molecule. It's a kind of large molecule called the phthalocyanine, which is a biologically related molecule. And these are the images. And we had no computer in those days, believe it or not. IBM, the greatest company in the world, we had no computer to actually measure the thing, so we used chart recordings. And we published that paper. And eventually, people started to believe you could see molecules. And by the time it came to, this is 97, so about 10 years later, we could even tell the shapes of molecules. So this is all one molecule, but it adopts different shapes because it's kind of bendy. And we could see these different shapes. And since then, there have been many, many studies, I mean, thousands and thousands of papers on STM imaging of molecules. So even though people tell you it's impossible, you know, and this is one of the things I learned at IBM and with Heine, is tell them. They may tell you it's impossible, but if you believe it truly, go ahead and do the experiment. And this is a front cover of Science where we saw a molecule, which is, maybe I will use the pointer, which is fixed here, and then it moves to the side and it starts to spin round, and we could see that with the microscope, and it was called a molecular wheel, and it was on the front cover of Science. And I also even received an award from a magazine called Wired. It's an American technological magazine, and many other awards actually. So it was quite amazing how this microscope, and later one that just used force, it didn't even need tunneling, it just felt the surface, could look at things on a single molecule basis. At least I thought a single molecule basis. By the time 2011, this is just an example of some work from a very nice Japanese scientist, Okawa, who we worked with. he was able to take a similar type of molecule and then actually generate a chemical reaction, called it polymerization, where a molecular wire shot towards one end of the molecule and attached to it. And then he shot a pulse of electricity on the other side and generated a molecular wire, which is something that people had dreamed about in the concept of making electronics from molecules for a long, long time. So what seems impossible does become possible. And I think, you know, if I was back in your days, I would like to have that vision. Imagine something that's impossible, totally impossible, and try to make it possible. Not an incremental change in the world. Another thing that happened about 30 years ago was we were always crashing into the surface with this microscope. And you see here at the top a kind of mesh surface, it's silver, and then we touched it and you see the little bump there. And I became intrigued by this, and we looked at a transition, it's called a transition from where the tip is far away from the surface, and the closer it gets to the surface, the current rises, and then there's a jump to contact. And at this contact point, it occurs a fundamental unit of conductance. It's like the inverse of the electrical resistance, a 2 e squared over h. H is Planck's constant, E is the electron charge. And that also stimulated probably 1,000 papers on quantized conduction. And Masa Iono, who's the director of the Materials Nanoarchitectonics program, and who was then, he set up the first ever government nanotechnology program called Atomcraft, was very interested in it. And you see, he got this beautiful result here where the resistance jumps in units of these quantized conduction units. And he did this actually using a silver surface which had sulfur on it. So if you take a spoon and you put it in an egg, a silver spoon, it will go black. That's the sulfite of the silver. And by applying a voltage, the silver atoms would jump through and make these single atom contacts. So it's very, very complex, but it's actually very simple. It's very reductionist in a way. So when I was in Japan working there, I asked the question, what happens if we make a lousy switch, a switch that's not perfect? And they said, well, we want to make a perfect switch. And I said, no, I'm interested in a condition where it sort of almost switches, but doesn't quite switch. What would happen then? And so I basically got bored, actually, with reductionism. I got really bored with it. And I thought, let's do something crazy. Just let's look at a switch that's a bad switch, not a good switch. And at that time, in UCLA, I'd started to work with the medical profession. So I met neuroscientists, pathologists, surgeons. I was working with them because I was interested to try to go into more complicated situations, and nothing that is more complicated in medicine, I guess, in terms of complexity. And I also started to change my kind of way of thinking through, firstly, Zen Buddhism. I'd spent some time in a Zen Buddhist kind of temple, getting up at 4 in the morning and things like that, and also doing art and science. And this is one art science piece I did together with an artist, Victoria Vesna. I've done many of them that kind of explore the idea between science and art. There lies something that's beyond, you know, the sort of dry kind of reductionist world. Well, anyway, back to the atom switch. So when we looked at the atom switch, this imperfect switch, where we put it into these conditions where it was totally imperfect, we started to see behavior that we could relate actually to a thing called the synapse. So in your brain, you have synapses, and they're very important. They have actually a relationship to the concept of learning. There's a model called the Atkinson-Schriffen model, which says that if you rehearse something many, many, many times, you will remember it. If you do it once, you will remember it for a minute and then you'll forget it. It's a characteristic of the human being, and it's related to the synaptic plasticity. So what we did was we showed that indeed if you infrequently pulse the thing, it kind of remembers and forgets. This is the change in conductivity we're measuring here. And the more you do it, it remembers a little bit longer. But if you do it very frequently, it remembers and stays in a permanent state. So we have an analogy here between what you would call a short-term memory and a long-term memory. And the sensory memory is the information appearing there. So we created a synapse, and we published that in Nature Materials. It is actually a material. It's a material that's synaptic and nanoscopic. And you can understand it in terms of forming tiny atomic bridges that have this quantized conduction. And if you make many pulses, it becomes thicker, and so it dissolves slower because it would like to go back to what you would call a thermodynamic stoichiometric equilibrium state. So this is the essence of the synaptic connection. Now, having done the synaptic connection, it seemed logical, let's do something else. And I thought, let's build the brain. If we have the synapses, how do we wire them up? And of course, most people, I guess, would think, well, let's make some kind of electronic circuit with, long wires, they go straight and so on, and then we can build something. But that's not how the brain looks. And it's very hard to build something with, say, a billion connections, a billion synaptic connections using even nanoelectronics today. So for that, we started our work on the brain. And one of the reasons that we're very interested to look at the brain is when you look at many phenomena that occur in the world, I would say most phenomena, they are no longer phenomena that are determined just by the property of one thing. They're determined by many things. They're determined by interactions. And so when you look at birds flying, they don't hit each other most of the time. They have a kind of self-organization and pattern formation. If you look at social networks like Facebook, if you look at the stock market, if you look at all of these different types of phenomena, then you see there is a kind of self-organization, power grids, earthquakes, they all follow this type of behavior, and the human brain's believed to follow it because the natural world around it doesn't exhibit this behavior. However, our brains do, and everything around us does, so it's very strange in physics that we hold on to the notion of a reductionist system. In RICAN, there is a very powerful computer. I think it's number 3 at the moment, but then they will revamp it and make it, try to bring it back to number 1. I think the Chinese is actually the most powerful computer in the world. And they tried to do a neuronal network, try to look at a neuronal network simulation. And they used all of this stuff. It took 40 minutes to simulate 1% of the human brain's activity. And it used 8.9 megawatts of power. That is the power for 10,000 homes. And yet our brain is capable to do that with a power of equivalently an electrical light bulb. So when we started to look at it, we looked actually at different types of models for the brain. And this part of the brain here, the neuropil, is part of the neocortex. It's 60% synapses by volume in the brain. And we thought, let us try to make this type of network. This is a picture by Cajal from the late 1800s, who actually used silver to stain samples and try to and obtain information about how these things are structured. And I worked with Walter Freeman, who actually works with rabbits. He looks at the electrical activity of rabbit brains and developed models for how the brain might function. So we took a complete departure and a big chance, and why not? because everything around us is connected, in my opinion, and it's the most important thing in the 21st century. It's the most important phenomena that determines so many things. I think I put a quote at the beginning. It was about Stephen Hawking, who said the 21st century is the century of complexity. And so it's a really important thing, but computers cannot predict it. So what we did was, we also looked at how the brain behaves. And if you look at, this is magnetic resonance imaging, you see a pattern formation in the brain that resembles very much clouds. It also is observed in neuronal cultures and also in these electrode measurements on the head, EEG measurements. And when you look at this data and you plot it in a certain way, as a logarithm versus a logarithm, exhibits straight lines. It doesn't follow the kind of statistical Gaussian normal distributions. It's completely different. It's an indication of self-organization. So we decided, let's build something that looks like that. And this is Henry Sillen, and he's a graduate student in my group. And we have a bunch of people like graduate students. And he is assembling here a kind of brain circuit. And the way we do it is to start with something that's ordered. And normally, you know, in science, you like to take something that's ordered and make something that's ordered. Or something that's disordered and make something that's ordered. So what we do is take copper posts, we put liquid on them that converts them into silver, essentially, and generates these wiggly lines here. And then we sulfurize them, and we are able to generate massive amounts of atomic switches, where every wire touches every other wire here is a synaptic connection. So this whole circuit here, it looks very biological, is our beginnings of the brain. And the idea is, with this project, is to use it like a brain. So we have electrodes underneath, and we can input information and output information. Now, most of you, I guess, if you were doing an experiment and you saw this type of behavior when we pass electricity through it, you would say, well, it's noise, it's crazy. This is not an experiment. You would like to have something nice and clean. But if you actually take this data, this is what we wanted to see, and you plot it, it exhibits this beautiful power law dependencies, which is indicative of this self-organization process. And the slope has some relevance in that if you look at people that are asleep or awake, the slope of their activity changes. If you look at people that have epilepsy, have an epileptic fit, you will find that slope changes. It's an indication of the activity, the self-organization in their brain. And we've been able also to change that by changing various parameters in the system. In addition to that, we also are able to look at stuff that we believe resembles those MRI pictures in the brain. That is, when you look at correlations between different parts here we measure, you see activity where things are correlated and then become uncorrelated. And some things are not correlated. So we have a distributed system. We have self-organization, and we have emergent properties that arise from a system, not because of those connections, but because we have a network of connections, a network of nonlinear connections. And anything like that does exhibit emergent properties. Stock markets, human beings in a room. So when I think back, actually, this is now a zoom back to 2002 when I was not thinking about brains in a direct way. How I thought we could never build a brain. I don't know if we will succeed in building a brain that can match our own intelligence. But with Heine Rohrer, this is Sir Mark Welling now, the three of us, we were in a think tank in Sardinia in Italy, and this was the conclusion we came up with, which was a challenge, a kind of global challenge, and the challenge was understand and communicate with the brain. So in a way, using this self-organization and this type of circuitry, perhaps we will be able to understand also about the brain, and maybe one day be able to actually connect such circuits to our brains. So in the end, I just want to show a few things. This is Lisa, who wanted to write UCLA and carbon monoxide atoms when she joined the lab when I came in 2001. And she succeeded. It took her 2 years. And then sometimes she thought she could never believe it. But I said, if you believe something enough, it will happen. And she did succeed. And from the UCLA webpage, a year or so ago, this picture appeared. I didn't even know about it. And it said, it's more than optimistic thinking, it's optimistic doing. And I would say that's a very important message in research. You have to be optimistic about your thinking, about what you can achieve in the world. And you have to be certainly imaginative and creative, but you also have to be optimistically doing things. And if you optimistically do things, the chances are you will succeed at least 10% of the time. 90% of the time, hopefully you don't succeed. Otherwise you're in the wrong field, or you're not doing something that's crazy enough that's going to make a big impact on the world. So to you students, I'd like to finish just words of a 63-year-old man, but from my experiences in UCLA and the marvelous experiences in IBM, is make the impossible possible. This is the goals. Don't believe in the status quo. Patience pays. Pick a boss. If you're going to go to, go on to do a Ph.D. or so, pick a boss who's going to get a Nobel Prize or something, and a very good laboratory. And I think the University of Tokyo is certainly a very good laboratory. I don't know who's going to get the Nobel Prize here, but somebody will, I'm sure. And this thing, I think, is so important. The most important thing in science to me for this century is everything is connected, and it's not a closed system like the past. We have to deal with open systems. Even the global interactions, the politics, every single thing, right down to the neuron, right down to the atoms that we deal with, are increasingly globally connected. And materials are too. Even a spring. You take a spring, just a spring, in gravitational wave sensors, you would think it would follow a simple rule. It's called Hooke's law. Like the force and the displacement are related. In actual fact, if you look at it very carefully, you'll find this self-organization due to entanglement of things called dislocations, defects in the material. And the last thing is, and Heine told me this, Heine Rohrer, and everybody in IBM tried to do it, have fun doing science. Or else do something else. Find another subject in your life. Don't bother doing science if you don't have fun. There's no point. You'll get nowhere, and you won't be really creative or inspired. So I finished with one last picture. 1 minute 15 seconds to go. At the time of the 90s, I was painting. Everybody was painting in IBM. Gerd was painting, Heine was painting. And I made this picture that's called Man Touches Atom. And this is the microscope, and I'm touching the microscope. And I used to think, he who controls this kind of controls the universe. Now I think it differently. This atom is connected to this hand, it's connected to this brain, and this brain is connected to all these people, and it's connected to the world. So there is no such thing as a single atom. It was an illusion all along, an illusion that still persists. And it's only when I was looking recently, I found this painting, which I never saw before, and it's Diego Rivera. It's called Man Controller of the Universe from 1934. Here's Lenin. This is communism on one side. This side is the time of the Rockefellers. It's the decadence. And there's lots of things in this painting, but the most interesting thing is, here is the man, and he has this deterministic, precise control. You could think of that, he's holding the atom. The world has changed. We're in the 21st century, and that no longer is true. But it's an old model, It's an industrial corporate model from the past. And I hope that you can embrace complexity. And through your interactions, the more interactions you have, the better. And the more you yourself will have a self-organization and a creativity. And don't limit it to other people in science. Try to talk to everyone, artists, scientists, neuroscientists, engineers, biologists, whoever, the man in the street. And with that, that's Lisa's work. This is what she wanted to do, and she did it. It took her a couple of years, and it took her 2 days to move it. Anyway, with that, I'd like to thank you, and I wish you guys up the best at the back of the room. A really great career, because you have the power to change Japan. The people here don't have any power to change Japan. Okay, thank you.